Muito bem. Very nice. So I would like to welcome you all to this afternoon session at IMPA. Today is a very interesting day. We are going to do, for the first time, a broadcast of a thesis defense at IMPA. We are now launching this new initiative, which I find very interesting. This is the first thesis defended in 2019, and it's being broadcasted live on our YouTube channel, and there's a large audience here. An initiative that I find very nice because all the friends and family of our PhD candidate today will be following from Peru. So let me explain to you a little bit on what's the usual steps of a PhD thesis defense here at IMPA, so we all are on the same step. So I will be doing a brief introduction of our PhD candidate today. He will have 50 minutes to do his presentation on his work, and after that, this will be followed by comments and questions of our committee, who's seated right here, and one member is outside following us in the United States. And after that, I will open the space to floors from the audience here, present here. Today, I'll not be opening to questions from YouTube. Let's see if maybe next time we'll do that. And then after that, I will invite everyone to leave the room for a little bit while the committee deliberates and reaches a decision on whether to approve or not our PhD candidate. After that, I will invite everyone back in the room, and during the deliberation moment, of course, the filming will be temporarily stopped. I will invite everyone back to the room, and then we'll deliver the final result of our thesis defense. Okay, so without further ado, let's start. This is the PhD thesis defense of Carlos Andrés Chirre Chávez from Peru, who's my PhD student. I am Emmanuel Carneiro. I'm his supervisor, one of the members of the committee today. Let me introduce to you the other members of our committee in this afternoon. So we have here Professor Misha Belolipetsky from IMPA. We have Professor Dimitar Dimitrov from Unesp in São Paulo. We have Professor Felipe Linares from IMPA, and Professor Carlos Gustavo Moreira, our dear Gugu, from IMPA. And following us in the United States, maybe we can put him here in the camera. Micah, do you hear us? Okay, maybe not. There he is. We have Professor Micah Milinovic in the United States, who's also part of our committee. So we are 6 members in the committee this afternoon. Andrés will be defending his thesis. His title of the thesis is Bounds for the Riemann zeta function via Fourier analysis. It's a nice work in the combination of analytic number theory and harmonic analysis. And I guess at this point, I will pass the floor to Andrés. He will have 50 minutes to do his presentation on his thesis work. Andrés, the floor is yours.
Okay, thank you so much. Thank you so much, everyone, for being here. Thank you so much, professors. Well, today I will do the defense of my thesis, bounds for the Riemann zeta function via Fourier analysis. And the idea here, the main goal, is to show new estimates for some objects related with the Riemann zeta functions using special machinery, for example, from harmonic analysis, approximation theory, and analytic number theory. So the thesis compiles the following papers that I did during my doctorate with my collaborators. The paper 1, paper 2, and 3 are estimates for some objects like as the argument of the Riemann zeta functions. The paper 4 is the opposite of the paper 1. Essentially, the philosophy is the opposite of the paper 1. And the paper 5 is a study of the zeros of the Riemann zeta functions using this special machinery semi-definite programming bounds. So I will divide the presentation in 3 parts. The first part, the idea is bounding zeta. Is like as I will use band limit approximation to obtain good bounds for some objects related with the Riemann zeta functions. Again, the second part is non-bounding zeta. I will use the resonance method to do the opposite in the part 1. And finally, the part 3 is a special study of the distribution of the zeros of the Riemann zeta functions using these special functions such that has Fourier transforms with special sign. So let me start defining our principal object here, the Riemann zeta function. So we know that in this set, real part S bigger than 1, we define the Riemann zeta function in this form, like as this series here. And using the special machinery, for example, the Poisson formula, we can extend the definition of the Riemann zeta function for the whole complex plane. So finally, we have a special function defined on the whole complex plane, but with this special point, this point is a pole, the point S equals 1. And the idea is to try to understand this special function. And one of the principal problems is to study the zeros of this function. So using Parsons analytic number theory, for example, we obtain information about the distribution of the zeros. For example, using this factorization in this part, we know that we don't have zeros in this set. Using a special functional equation, we don't have zeros in this set, but we have only zeros, simple zeros in this point, -2, -4, -6, etc. So this is the trivial zeros of the Riemann zeta functions. These are the trivial zeros of the Riemann zeta function. And the problem is in this special set. This is the critical strip. And the idea is to understand the zeros in this part. And one of the most important conjectures is the Riemann hypothesis. And the Riemann hypothesis say, okay, all non-trivial zeros in this critical strip lie in this critical line. So essentially, this is a graphic of the situation here of the zeros. All the zeros lie in this line. So from now on, we assume the Riemann hypothesis for our theorems here. Let me start defining this special object. So we have this special formula, the Riemann-Born-Mangold formula, that states the number of zeros with ordinate smaller than t. So essentially, you can count the number of zeros in this rectangle here. And this is the formula that we have. Nt is t over 2 pi log t over 2 pi minus t over 2 pi plus 7 over 8, plus a special object here, the argument function, plus the error term. And this is the argument function, so we define this argument in this form. You start in this point 2, and you move along this line, and you calculate the variation of the argument in this line. And this is the definition of the argument of the Riemann zeta function in this point, 1 over 2 plus at, with this constant. This is our function st. And we define the high moments or the antiderivative of the function s0. For example, the function s1 is the integral of the function s plus a special constant. S2 is the integral of s1 plus a specific constant. And I would like to study these functions because we have this nice theorem of Fuji in 2001. And he established the following. The Riemann hypothesis is equivalent to have this special behavior. S nt over t power n minus 2 goes to 0 when t goes to infinity, when n is bigger than 3. This equivalent of the Riemann zeta function inspired to try to understand the behavior of this function and show special bounds for these nice functions. So while we start with this part, bounding zeta, specifically the paper 1, using band limit approximations. So a classical result of Littlewood in 1924 states the following. Under the Riemann hypothesis, we have this inequality here. The function s and t are bounded by this a special function log t over log t power n plus 1. And we have this special constant here. And over the last 90 years, the order of magnitude has not been improved. So the idea now is to show nice constant. The idea is to show good constant that you can put here in this inequality. This is the first idea in one of the problems here. For example, the case n equals 0. Under the Riemann hypothesis, we have this result established by Littlewood, and the idea is to put a nice constant here, a good constant here. So, for example, Ramachandra and Sankararayan in 1993, they showed this constant 1.119. It was improved by Fuji in 2004 with this constant 0.67. Gosson and Gonding improved this constant with 0.5. And recently, Carneros and Milinovich established these new constants, 0.25. This is the case n equals 0. The case n equals 1. Again, we have the bounds by Littlewood, and the idea is to put good constants here. For example, Karatsuba and Korolev in 2005 showed this constant, 40 minus 40. Fuji improved the result with these constants. And finally, Carnero and Milinovich showed these special constants here, 0.065 and minus 0.130. This is an approximation because this is the real constant here. What's happening in the case n bigger than 2? So again, we have the inequality, the bound established by Littlewood, and the idea is to show good constants here. Wakasa in 2012, he showed this constant, these special sums with this factorial here. A, B, C are universal constants. And he showed this constant here, and these constants are special because these constants go to this number, 0.3203. One of the results that I have with my advisor Emmanuel Carneiro is the following. Assume the Riemann hypothesis. So again, this is the behavior established by Littlewood, and the idea is to put good constant. And in this case, we obtain these special constants. For example, the case n equals 1 mod 4, you can put these special constants here. And this constant depends only in the values of the Riemann zeta function in these special points. In this case, like as 4k plus 2, so it's an even integer here. In the case of n equals 3 mod 4, you inverse the result. And for n bigger than 2, even, the constant Cn is a combination of the previous constant and the next constant. And these constants are very special because this constant goes to zeros with exponential decay. So we improve the previous result of Wakasa here. I would like to give you an idea of the proof. I will fix a natural number n odd. And the first idea is to try to obtain a special representation of the function SNT. Because until now, we only know this information. The function SNT is the integral of the other function plus a special constant. So using a special machinery in analytic number theory, for example, Adamar factorization, assuming the Riemann hypothesis, we have this representation. The function SNT, you can write in this form. This number depends on n log t minus this number multiply this special sum here plus the error term. Okay, this is a good representation because we can understand this term and this term, the error term. But the problem is this part because this is a sum. It's a sum, and this sum ranks over the ordinates of the non-trivial zeros of the Riemann zeta function. All the zeros in this special critical line here. This is the first problem. Try to understand this sum. And the other problem is this function, because this function is not trivial. For example, the case n equals 1, you have this function. f1x is 1 minus x arctan 1 over x. Complicated. The function f3 is more complicated. The function f5 more complicated. The function f7 is more complicated. By induction, all the functions are complicated. And how can we understand this part? Because the functions are complicated. Happily for us, we have a special formula in analytic number theory, the Ginnan-Well explicit formula, that says the following. Assume Riemann hypothesis Riemann hypothesis. So take a function h with some properties. This function is analytic in some strip, and this function has this decay. So I can give you this special sum, and this sum appears here, right? When with a translation here. And this sum is this term plus minus this special term plus the error. So, well, we have the von Manuel function here, the arithmetic function here, and we have the Fourier transform of the function h here. This is the gamma function here. So, we can use this Ginn-Well explicit formula here to try to understand this sum. We can use this part, we can use the formula, you can do the computation and you obtain the result. This is the first idea, right? But we have a big problem here. The most difficult problem here is that these functions are very complicated, and in particular these functions doesn't satisfy this condition here. So we cannot use the Ginn-Well explicit formula now. Wow, difficult problem. So let me write this part again. The function Snt, you can write in this form. Special constant depends on n, log t, plus minus, no problem. Special constant of n, this special sum, plus the error obtained here. And the idea is to replace this function fn, with other special functions, h. And this function, it will be very nice if this function satisfies this condition, right? And you can use again a Well explicit formula here. So this is the first idea. I will replace this function here with other special function h. And we want to establish an inequality here, so no problem if you have this type of inequality here, because in this case, you create an inequality here. You have an inequality here. That same term here, log t, plus this constant here, this sum, plus the error term here. And I would like to obtain this function h such that satisfies these conditions here. So this is our problem now. For this function fn, the idea is to find another special function h with this property, with these properties, first part. The second part is the following. We want to use the Ginn-Well explicit formula, but, well, this part you can understand using Stirling formula, for example. The error, no problem. The problem is this series, because it's an infinity sum, right? So it will be very nice if the Fourier transform of the function h has compact support, because in this case, this series now is a finite sum, and you can use, for example, the prime number theorem to estimate this part. So this is one of the second properties that I want. The first, second, and finally a technical property is the following. I would like to minimize the distance L1 here of this function here. And these three properties here essentially is the Berlin-Selberg problem. It's a classical problem in approximation theory. If I have a special function f, the idea is to find a function h with these properties. Berlin and Selberg solved this problem for these special functions. For example, in 1930, Berlin solved this problem with the signum function, and Selberg solved this problem with a characteristic function here. And for example, during this time, we have other type of result in this form. And for example, we have this nice theorem of Carnero, Lindman, and Baller. They show the following. Is this function f has this form, is the integral of the Gaussian with a special measure, and this measure satisfies this condition. So you solve the Berlin-Selberg problem for this function f. Okay, so we have this theorem, and I would like to use this theorem with this part. So it would be very nice if the function fn has this form. And this is exactly that we have, because this function fn, that are terrible, right? This function has this form, is the integral of the Gaussian with this special measure. And this measure is terrible too. But no problem, because this measure satisfies these conditions. So nice, because this function you can write in this form. You can use the theorem of Carnero, Riemann, and Baller. You obtain this function h, and you replace the function fn with this function h. You can use the Guinan-Well explicit formula here. You estimate this part with the Stirling formula that order no problem, and this part is a finite sum because the Fourier transform of h has composite support. So finally, you can do the computation here, and you obtain the inequality for the function SNT. This is the idea of the proof in the case n odd. What happens when n is even? When n is even is different because we don't have an equivalent result for a special function fn. Okay, you can write the function SNT in the case of n even. You can write in a similar form of this. Again, the idea is to replace this function with other special function here, but the problem is that we don't have the solution of this problem for this special function f2, f4, f6. So we need to use other idea in this part, and this is idea. N is a even natural number. We want to establish bounds for S and T. But you have information about Sn minus 1, and you have information about Sn plus 1. Because in this case, n minus 1 and n plus 1 are odd number, right? But what is the relation between S and T, Sn minus 1 and Sn plus 1? Is the following, is the definition of the function. Sn minus 1 is the derivative of the function Snt, and Sn plus 1 is the integral of the function Sn plus a constant. So essentially, the problem is the following. We want to establish bounds for Snt, and you have inequalities in this form for this function, for the derivative, and you have inequalities for the integral. So now you can forget analytic number theory, you can forget harmonic analysis, approximation theory, and you find this problem like as a problem in real analysis. So for example, and you can use mean value theorem, you can use some function optimization to obtain nice constants here, and finally you obtain the result. For this reason, the constant Cn for the case n even depends on the constant Cn minus 1 and Cn plus 1. And we obtain the result for Snt. This is the paper 1. The paper 2, we extend these previous results, but now in the critical strip. So essentially, the idea is the following. You have a special point now, not here, now in sigma plus at, when sigma lies in 1/2 and 1 in this interval. So you can calculate the variation of the argument here. You define the function as sigma. You can define the function as n. And we obtain similar results now in the critical strip.
Andrés, this is all on Riemann hypothesis, right?
Yes. This result is assuming the Riemann hypothesis. In particular, we obtain new proofs for the bounds of St and the logarithm of the modulus of the Riemann zeta function in a point in the critical line. And in the paper 3, we extend the results now for a special family of L-functions, specific, for example, entire L-functions. But this is the idea in the papers 1, 2, and 3. Use this special band limit approximation here. Let me talk about the paper 4, non-bonding zeta. Let me say why I do this non-bonding. I will use the resonance method to try to non-bonding zeta. Let me start what's happening here. Let me start, I will say what's happening here. So, we have the result that we establish, well, we have the result of Littlewood. S and t is bound with a special constant, I will write this form, plus the root term, log t power log t over log t power n plus 1. And for example, the case n equals 0, you can write the function log t over log t. The case equals 0, so this is log t over log t. So I will try to do a graphic of these functions. Suppose that this is like something like this, log t over log t, with this constant c0. I will write the same here, log t over log t. So I will try to write the function s0, st. And this information, this inequality, tell me the following. The function has this behavior, lie in this part, right? This is an inequality. So the graphic of the function is in this part. But maybe these bounds really are very bad. Maybe the function is decreasing, for example. Or maybe it's more simple. The idea is to say, no, this function is very difficult. This function has a different behavior, a more complicated behavior. For example, Montgomery in 1977, he established the following. There is a positive constant C0 such that for arbitrarily large t, you have this result. So I would like to do the graphic again. Suppose that this is the graphic of, this is other C0, right? This is 1 over 4. I will put this C0 here, log t over log t. With this power, 1 over 2, 1 over 2. And the Montgomery say the following. The graphic of the function st is smaller than this, but it's now, you can do the graphic in this form. So many times, this function could in this part is bigger of this function here. So we can say this function st is not trivial. This function many times has a special behavior here. This is the idea in this type of inequalities. The other case is the same, right? It's symmetric. For example, Zhang is a student of Selber.
I think it's nice to mention that this is for a sequence of arbitrarily large t. A sequence.
It's not for all t. Yes.
For all t, but just for
Many times it's bigger, right?
for a certain sequence of t going to infinity.
Yes. Well, yes. A similar result we have in this case for the function s1. Again, the function s1, now we have a special constant here, and we have the power 2 here. And again, the function s1, you can write the function. Suppose that this function, the graphic is something of this. And these results say that the function is not trivial. The function has a special behavior some moments, because many times the function s2 is bigger than this. So for example, if I do the graphic of this, I would like to write here c1 log t, 1 over 2 over log t, 3 over 2. And essentially the function s1 many times is bigger to this function. Not for all t especially. For a special sequence of tn goes to infinity. This is the idea of the result here. For the reason I say no, it's not bounding, right? It's other type of bounds here. And we have the following theorem here. So we can extend the result for all ascent. And we have this type of lower bound now here for an infinity sequence of Tn, you have this inequality. Von der Recon showed this inequality for the case n equals 0 and n equals 1. And the result, for example, the n equals 0, you have log t power of 1 over 2, log t power 1 over 2 over log t 1 over 2. And in some sense, this result improves the result of Montgomery. Now we add a new term, log t. So essentially, this function is more bigger. And I extend these results for all cases n bigger than 2. We can find these ideas now for the critical strip. For example, again, you define the argument of the Riemann zeta function in this point. You define the special function Sn sigma t with this definition. For example, in the n equals 0, we have the result of Zhang again. You have this type of lower bound. Let me do a graphic here now. And this result is when sigma is close to the critical line. So in this case, sigma line this part here. So you are close to the critical line, and you can obtain these lower bounds for this supremum of the argument of the Riemann zeta function here, with this special interval t lie in capital T to capital T. We have this result too, assume Riemann hypothesis, and again, your sigma lies in this here, in this special set close to the critical line. And again, you can obtain this type of estimates for the supremum of these functions in a special interval, and we have this form here. And essentially, in some sense, we improve the result of Zhang, because again, Zhang have log t power 1 over 2 over log t 1 over 2, and the philosophy is that we add this new term, log t, here. Let me give you an idea of the proof about this. I will use the classical resonance method of Sonderayang, but in a special version of Bondarenko shape. The idea is the following. You have the special object, the function is sigma t, and the idea is to multiply this object with a Dirichlet polynomial here. But the idea is to choose a good polynomial here such that you pick large values of this special function. Let me give you an example. Well, we define the resonator, the modulus of the Dirichlet polynomial, power 2. And this is a Dirichlet polynomial classical, so this is the sum over a special subset of integers. And we have an arithmetic function here over n power it. Let me give you an example. For example, this is the method of Sonderayang, the first idea of the resonance methods. You take a special function phi, a positive function with compact support in this interval, 1, 2. And we want to bound this quotient here, this ratio here. This is the idea. So, okay, this function has compact support 1, 2, so essentially this is t over capital T, so essentially this integral lies in t to, well, capital T to capital T. So you can estimate the numerator here. You take this part like a supremum of this function here in this interval. You have the other part here, and you complete the integral again, and the integral is cancelled with this, so you have this type of estimates. And the idea is, if you want to establish good lower bounds for this function, you need to establish a good lower bounds for this quotient here. So the idea is try to optimize this part here. But for example, in this case, well, the Riemann zeta function, you can express this Riemann zeta function like as a finite sum using some approximations. And this is a Dirichlet polynomial here. So essentially we have, if you do the computation, you have a quadratic form here. Here you have again the quadratic form. So essentially you need to optimize the quotient of two quadratic forms. This is the first idea of Sonderayang. But for our function Sn, we need to do something different here. I will explore the case n equals 3 mod 4. You start with this function k in this form, minus log t phi 2 pi log t x. And this function phi now is not a function with compact support, now is the Gaussian function. And now the idea is to estimate this integral here. So again, the first idea is to take the modulus here. You pass here the modulus here. And for example, this part here, you can bound, like I said, this idea, right? You try to do this idea. So you can bound the function Sn sigma t using this type of estimates. We have this estimate here. So you divide this integral here in 3 parts, these special intervals, and in this interval you can use this type of estimate here, and you need to identify the main term and the error term. And the main term is exactly the part where these values here lie in a special interval. For this reason, we have this special interval here. The supremum now is not capital T to capital T. Now it's a special integral because we have now this integral here. And because we have the Gaussian function here, so we have this type of supremum now. Again, you use this part cancel with this, so essentially you have here in this part, this is less than the supremum of the function Sn in a special interval. And again, the idea is to try to obtain lower bounds for this or optimize this part. And how this integral is good? Because in our case, assume the Riemann hypothesis in the critical strip, for our special function Sn, we have this type of representation. The integral, this part here, is exactly 1 over pi, and the real part of this special sum. This special bound again depends on the von Mansell functions. Here sigma, here's this term, and we have now the Fourier transform of the kernel k here, and the error term. So the idea is to use this formula here to replace this part here, and try to obtain a lower bound for this. But we have a new problem now because now we have an integral of a sum of von Mansell, the Fourier transform of k, and this type of the Dirichlet polynomial and the Gaussian here. But we have this principal lemma here. If you have this situation, if you have that a special function gt with this is like a series, von Mansell function here, am, and sigma plus at log m. So you can put this function gt. This is the special part of the Dirichlet polynomial and the Gaussian function. So this integral, you can obtain a special lower bound in this case. And well, this lemma is very important. It's very important, and essentially in this part appears the special election of the Dirichlet polynomial. You need to take a special Dirichlet polynomial using combinatory arguments to try to obtain this type of lower bounds. And this term t and this term is cancelled with this part. So essentially, for this reason, you obtain this type of estimate in the lower bound. And well, using this, we obtain this type of result here. But this is the idea in the paper 4. Let me start with the final part, paper 5, and a special study of the distribution of the zeros of the Riemann zeta functions using a special function Fourier transform with sign. Okay, let me write here. The idea now is to use a new special function here. So, in the first part, in the paper 1, we use a special function, band limit approximation. And this function, for example, this function has compact support. The Fourier transform has compact support. So the Fourier transform is 0 outside this interval. And these functions are very special in analytic number theory because we can obtain a lot of results in, for example, in the percolation of the zeros of the Riemann zeta function, we obtain estimates for the argument of the Riemann zeta function, for the logarithm, for other special functions. You can study the distribution of the zeros using these special functions. But the idea now is to chain these functions with other special functions. For example, in this paper, well, in that work of Chirre pecking in dimension 8 and 24, Vyazovska, Kohn, Kuma, Miller, and Lachenko solved this problem of Chirre pecking, but in this case they used this special function with a special sign. It's not positive when t is bigger than 1. In this work, Fourier optimization and prime gas, Carnero, Milinovich, and Sonderrayan, again, they used these special functions to obtain nice results in prime gaps. And the idea now is to try to construct this function. Because, for example, when we have this part, when we have these functions, we have a lot of theory about this. We can use blank space, we can use Paley-Wiener theorem, but construct this function is more difficult. We have some machinery here, for example, modular forms, construction with distributions, linear programming bounds, and semi-definite programming bounds. And these are the techniques that we have now. The idea is how can we use these functions to obtain nice results in analytic number theory. Let me start talking about the percolation of the zeros of the Riemann zeta function. Montgomery, in 1973, he defined this function, the function f alpha, well, really is f alpha t, this is the number of zeros with the imaginary part smaller than t, multiply this sum, and this sum run over the pair of ordinates of the zeros of the Riemann zeta function, non-trivial zeros. We have this exponential term, and we have this way here. This way is exactly this type of way, 4 over 4 plus u power 2. And one of the nice results of Montgomery is the following. This theorem of Montgomery, assume Riemann hypothesis, and this function has these properties. This function is even, this function is positive, and I can give you the behavior of this function here, but only in this interval, minus 1, 1. This is one of the nice results of Montgomery. And how can we use this to obtain that result? Let me define this special function here, the function n star t, in this form. Okay, I would like to establish inequalities for this function. Well, it's easy to see that this function n star is bigger than nt, because the multiplicity is bigger than 1, so you have this inequality without problem. So in a beautiful world, you have this. In this case, you can say that all zeros of the Riemann zeta function are simples, right? But this is the beautiful world. It's not, well, until now we don't have nothing about this. But I would like to establish the other inequalities here in the other part. So I would like to establish inequalities, something like this. Again, the beautiful word is when C is 1, C equals 1. I would like to establish good bounds for this constant here. And the idea of Montgomery is the following. He used this relation, and in this relation we have the function f here. We have this special spacing of the zeros of the Riemann zeta function, and we have a special function g here, appearing here. So let me use this special formula to establish bound in this form. So left-hand side. On the left-hand side, we have the following. We have this part. So we assume first, we assume that G and the Fourier transform of G lie in L1. I need to assume this to establish this equality here first. Second, let me put the function G is positive with these properties. I will try to obtain this type of inequalities using these properties here. So, okay, the function G is positive, and this way is positive. So, this sum is over all over the pairs of the zeros of the Riemann zeta function. So, you can obtain a lower bound of this part in this form. You can only sum this part, but only when gamma is equals gamma prime. And we have again this gamma gamma log t over 2 pi, the weight gamma minus gamma prime. Okay, but when gamma is gamma prime, so you have essentially here 0. So this is G0. This weight is double 0, so it's 1. The definition of the W is this, so it's 1. And finally, we have this type of sum. Gamma prime here. And if you count this type of sum, counting with multiplicity, so you have finally G0 multiplied this function n star t here. Okay, we have this first inequality in this part. So let me use this part now, right hand side. And this is the nt, the integral of the Fourier transform of G f alpha t. So now here appears the idea of Montgomery. You can see that you have n star t, this type of inequality, and you want to establish, when you have nt here, and you want to obtain a constant here, a good constant here. But the idea of Montgomery is the following. You have the information of the function f in this interval. So for this reason, you need to put a special function g with these properties, but we have only information in this interval. So Montgomery used the following idea. They put other condition for this function, and they say, okay, the function has the Fourier transform is 0 outside the interval 1, 1. Using this condition, this part now is nt minus 1, 1, right? Because it's 0 outside. So minus 1, 1, the Fourier transform of G. Let me write in this form, nt plus nt. So using this condition here, this part is 0. So essentially you have, again, nt minus 1, 1, the Fourier transform of G. And now you have the information about the function f in this interval. So you can do the computation here, and you obtain something like this. Finally, we have the following. G0 multiply n star t is smaller, it's small, when it's smaller than this part here. And this is nt here, and this is the constant that I would like to put here. Well, you need to divide G0 in this part, right? And this is the idea of Montgomery, and Montgomery put a special function here and he obtained this result. Assuming Riemann hypothesis, we have the following: n star t is smaller than a constant multiplying t, and Montgomery with this special kernel sin px or px or 2. This function satisfies this condition here, here, and here. And Montgomery obtained this result, 1.333. Really, he obtained 4/3. Montgomery and Taylor improved the result in the following form. He divided this part here, G0, and he tried to minimize this functional here depends of G with these conditions, first, second, until here. And they optimized this part, and they obtained 1.3275. And then we have the result of Chirre and Goldstone. They use the part that you lost here, and they improve this result 1.327, and he improved in this term 5 to 2. Well, you 19 years, and we have this improved here. Well, they use a nice combinatory argument here to use this part that you lost. And recently, with Gonsalves and Delat, we obtained a new result here. And let me talk about the idea here. Okay. Again, we have this part, no problem with this. This is an inequality because you lost the other part of the sum. No problem here. And here appears the idea that we have. Okay, Montgomery, in the theorem of Montgomery, they say this information about alpha in -1, 1. The idea is the following. This condition is very strong because you want to establish an inequality here. So the idea is the following. This function f is positive. It's positive on the real line. So if you input a new condition here in this form, with this inequality here, this is negative. So again, you lost this part, and you can put now here an inequality because this is negative. And the calculus is the same. So again, we have the following. G0 and star t, smaller, small here, and we have again the same. Again, you can divide G0 and you put here. And the idea is to construct a function G with these properties. These properties here and these new properties here. The Fourier transform with special sign. And this is the idea, to try to construct this type of objects. And with Gonsalves and Delat, we construct this object. For this reason, we improve the previous result here, 1.3208. And essentially, the function that we put here is a special polynomial here, the Gaussian function here, and this polynomial has degree like as 82. It's a difficult polynomial here. And we obtain the result here. Using the function n star, we can obtain estimates for the number of distinct zeros of the Riemann zeta function. So using some tricks, we can, under the Riemann hypothesis, now we establish the following. The number of zeros of the Riemann zeta function in percentage is at least 84.77%. And this is one of the results that we have with my collaborators. And essentially, in the same paper, we proved similar results for the percentage of simple zeros of the family of Dirichlet polynomial of the family of primitive Dirichlet L functions. And we have similar results and similar estimates for the derivative of the function chi. The idea, again, is to try to construct this special function with these properties here and other special properties that appear in the works. Okay, thank you so much.
Okay, Andrés, thank you very much for your presentation. We now move to the next stage where we are going to open the floor to questions and comments from the members of the committee. Without no particular order attached, just the one closest to me. How about we start with you, Misha? Is that okay? No, you can be seated.
I can stand up.
There's a camera there for you, Misha, so you can be seated.
Okay. Which camera? This is okay. Well, thank you, Andres, for very interesting thesis and very nice presentation. I enjoyed it a lot. The last chapter, so chapter 6, which is article 5, is closer to my interest. So I'm going to maybe ask something or make a comment about this. Well, first I wanted to mention, I said it to someone else some time ago, that when you cite Kohn and Elke's paper, I think you should also cite Gorbachev's paper, who proved the same, or essentially the same theorem at the same time, just he published it in university journal, but okay. Kohn and Elke's cite Gorbachev, but then people forget about his work. It's unfair because he proved the same result, only he didn't publish it in annals, and it's. I strongly recommend you to cite it in the paper and in the thesis. This is a strong, small comment, and just curiosity. I mean, you in your bounds, which appeared, I think, in the previous slide. So there is there is this sequence of improvements. So is there some natural bound for this method, like 1.3 or 1.2, or you may expect to get close to 1 by some, I don't know, some miraculous choice of functions? Or what do you think about it?
The expectation about a good constant here.
So the conjecture is that C is equal to 1, or
yes, exactly.
arbitrarily close to 1. So then you have Montgomery method, which you plug some function and you get a constant.
Yes.
So do you expect that there exists some function or sequence of functions which you will plug and get arbitrarily close to 1? Or there is some natural bound, just Montgomery doesn't allow you to get?
I think that no, but let me think a special answer in this case. Well, using this idea of Montgomery, you lost a lot of information here, right?
Right.
But this is the principal problem here.
But that happens with sphere packings as well. When you do Koinelskis, you kind of lose a lot of information. But surprisingly, at least in dimensions 8 and 24, you at the end you don't lose anything. So this is the miracle of the.
Yes, yes. In the case of the dimension 8 and 24, it's amazing because they use this type of algorithms to obtain the result of the problem sphere packing, right? We try to use the same argument of Henry and Cohn's, but we cannot use this argument because we lost some control about the root of the polynomial here. So for this reason, we change the method and we use semi-definite programming bounds because the method of Henry and Kohn is linear programming bounds. And unfortunately, the lads worked in similar problems of sphere packing, and he used other techniques, especially of semi-definite programming bounds. And these techniques are different. The methods, the algorithms are different compared with Kohn and Helkis. And really, we don't expect that we can obtain more of this because the idea is essentially to divide this G0 here, right, and optimize this part. But using these methods, we cannot optimize this part. But in sphere packing appears the optimization of this part.
But you always work with the function Gaussian multiplied by polynomial. So that is like one can, well,
Well, we
I
use
can
this.
try other function.
Yes, I agree with you. This special function we use it because, for example, these functions are eigenvalues of a special functional using Laguerre functions. So for the reason we use these special functions here because we have some control about this function and the Fourier transform of this, right? Because the Fourier transform is like other polynomial here and exponential. So we have some control about the sign of this function here because it's one of the conditions, right? Yes, but we are not expect that this is the optimized form to obtain this type of result.
I would like to maybe complement his answer, I think, to your nice question is that once you set up an optimization problem, I mean, his argument sets up an optimization problem, which is a different problem than the original one proposed by Montgomery. Montgomery proposed a problem when he had band-limited functions. So first he used the sine pi x over pi x squared as a first good approximation, and then he realized that it was not optimal and he could actually find the optimal thing. So here in this line of argument, they relaxed the condition on the Fourier transform for just having a sign outside one, and they set up a new optimization problem. So you have to optimize a certain quantity in a certain class of functions. Well, this is a harder optimization problem because you're working on a bigger class. But this approach of approximating by polynomials times Gaussians, this is essentially using one of the bases of L2, which is the Hermite basis. And the fact that they get a polynomial of degree 82 is pretty much, it's not the optimal solution for the problem. The actual optimal solution for this problem might be a very hard thing to do, but this is actually very, very close to the solution. Like Kohn and Elkis, they could not solve the sphere packing dimensions in the 24, but their simulations already got to the 50 decimal places of the right answer. So Vyazovsky actually improved in the fifth decimal place, let's put it this way. They knew that the answer was correct up to 50 decimal places. 50, I say 50. But here, it's very unlikely that there's a magic function for this optimization problem that gives you the answer 1. You might be able to improve a little bit on the 5th, 6th digit, and so on. But so to answer your question, for this particular optimization problem with 99.9%, the answer is no. Mm-hmm. But you could, of course, set up a different method, set up a different optimization problem to capture a little bit more of the information on the zeros that you're losing there that might lead to better improvements. But this is, of course, very, very, very hard.
Okay, thank you very much. So, well, I will pass to...
So if you're done with the questions, we now pass to Professor Dimitar Dimitrov from UNESP.
First of all, thank you, Emmanuel and Andrés, for the invitation. I was going to say something which was, when I was writing my thesis, there was a booklet circulating among the PhD students, and there were some advices. It was saying, don't write too long because you are not Lev Tolstoy and this is not War and Peace. Don't write too short because you are not Einstein and this is not the theory of relativity. And if you write either too long or too short, this would mean that you are either genius or fool. And the committee will forgive you none of these. But I tend to forgive you because I like very much the thesis. So it's really a very nice thesis, very deep, technically very strong. You really obviously don't feel any fear of doing very hard calculations, very deep calculations, and you learned and applied also very deep methods to your problems. And I have some principal questions already to an expert, obviously, in this area. My first question is about equivalence of the Riemann hypothesis of Fujii and your conditional results. And I understood more or less the answer of this question in a conversation with Emmanuel, but I was planning to ask you this question, so I'll do. Why this condition is so far away from your conditional results? Because usually when you have some conditions for the Riemann hypothesis, they are very close to the conditional results. And in this case, this is too far. There are logs there and you have powers here.
So really, for example, I would try to explain the idea of this. Really, Fuji in the paper, he showed a representation for this function Sn. In his case, the representation is something like this. I don't remember exactly the representation because it's more complicated, but it's something like this. I don't remember exactly. It's something like this, the representation of Fuji. This result is unconditional. And essentially, the idea is the following, right? These zeros, this sum is over the zeros. And this, the real part of these zeros, I will write this form, right? And these zeros, are outside of the critical line. So essentially, the equivalent is follows from this. The Riemann hypothesis equivalent to kill this part, and you lost a lot of information here, and you obtain this part assumed Riemann hypothesis, and the calculus that we have this about the function Sn, the estimates of the function Sn, essentially appear from this part.
So the best unconditional results are like a constant time to the -2.
Over something log t or something like this. I don't remember exactly the expression here. Maybe I feel log t, but it's something like
If
this.
it's over something which tends to infinity, then it implies Riemann hypothesis.
Yes.
So it cannot be better than constant time.
Yes. I don't remember exactly here appear here because it's something like k and other type of sound.
Okay.
Yes, something like this. But essentially, this is the part. The part unconditional appear here. And you lost the information when you assume Riemann hypothesis. So this part is very long for this part, right? So essentially, this you lost the information in this type of bound here.
There's also the secret delta N there.
I'm trying to find the page for my next question. So there's a problem, writing too long. My question is about, you mentioned somewhere a result of Gonek and co-authors that they have a conjecture about the exact value of a lim
ST.
sup about S of t. Yes. Okay, that's the one. Are there any similar conjectures for the modulus? What is the exact behavior of the zeta function on the critical line? In the sense, what is the truth about the Lindelof conjecture?
This is a good question.
Because this says what is expected to be the truth about S.
Yes, yes.
So my question is, what is expected to be the truth about the proper zeta function?
Yes.
Are there any conjectures?
Yes. Really, I didn't read in the literature about this, about that specific conjecture of ST. For example, in the book of Ibis, Alexander Ibis, the unique conjecture that he mentions about ST is this. Well, this is a result of Dyson and other guys using random matrix theory.
Yeah.
This is the unique conjecture that I see about the exactly behavior or the expectation about the function ST, a specific equality here.
Yeah.
But other type of conjectures exactly in this form, I didn't read exactly until now. Yes, I didn't read.
It's very likely that there is one. Usually these results for S of t, they
Imply.
come after what people have studied for modules.
Yeah.
Modules and the argument of the two things that people look into. But I would say yes, but I'm not sure. Maybe Micah at the end can help us.
Yes.
Okay. And something, I have some other very short observations. Once you gave a talk about one of your first results, I mentioned that in real analysis, there are classical inequalities estimating an intermediate derivative in terms of two neighboring derivatives. And these inequalities are very famous, and they are called Landau-Kolmogorov type inequalities. You can estimate, say, the first derivative in many norms in terms of the function itself and the second derivative. So you could have used this kind of classical
This type of
inequalities.
idea to relate the derivative, this function, right? Sn minus 1, Sn plus 1.
Yes, yes. But for the intermediate ones, there are classical inequalities. They're called Landau-Kolmogorov. You may learn a bit about them. And finally, about the derivative of the psi function. I like very much psi function, and there is something very interesting about it, because there was a very famous classical conjecture, the Riemann conjecture, which was proved first by Chávez and co-authors. And it says that if you have an entire function of order at most 2 with eventually finite number of zeros, after differentiating certain times, certain order of derivatives will already have only real zeros. This shows that the real line attracts the zeros of real entire functions of order at most 2. And the behavior of when the entire function is of order bigger than 2 is completely opposite. The real line repels the zeros when you differentiate. So you may try to eventually estimate the number of zeros of high derivatives of psi to see if you eventually prove that for the 10, the derivative, all the zeros will be real, or this percentage will go to 100%. Because if you suppose that the Riemann hypothesis, this means that you have that the Riemann psi function has only real zeros. So the number of the zeros of the first derivative will be equal to the number of the zeros of the psi function itself, because they come simply from the Rolle's theorem. So then the question about multiplicity still stays, but you may have in mind this problem and try to explore it more.
Yes, yes.
Congratulations, great thesis indeed. Thank you very much.
Thank you, Professor.
Thank you, Dimitar. Let's now pass the word to Professor Felipe Linares here from IMPA.
Thank you, Emmanuel. Okay, so I like very much the thesis of Carlos. It was very nice. I think he learned a lot of things. And, well, a little bit far from this stuff, right? But I would like to know a little bit more about this. What is the spirit of this part? You talk about unboundedness of this function. I didn't get it right, because it's like you say for any t you get a large T, but actually you are doing this in a discrete way, right? This is what you are saying.
Yes.
But then you are worried about to be bound, right? So what is that for? What do you want to know?
Explain to people what are these omega results, what it means.
Okay. Let me do that right again. Okay, when I read this part of the omega results and the resonance method, the idea that I have is something like this, like, so, for example, the argument functions, the graphic of the argument function really is something like this. Let me write there. Something like this. And so we have estimate in this case for st, something like this, log t over log t. But this function st, how can I say, has a lot of power of cancellation. And the idea is to try this cancellation, how you can use this cancellation. And for example, one of these results states that the cancellation appears, for example, the estimate of the function st is something like this. The estimate of S1, that is the integral of S, is something like this. Over 2. So essentially, we have some cancellation here. But these bounds that we have now, really, over the last 90 years, we have only this type of order of magnitude here. And the idea to try to show this result is to say that, okay, the function st is oscillatory. So really, we cannot write the function s in t something like this: principal term plus error term, something like error. So it's not easy to try to write the function s in t in this form, because the function is oscillatory. It's very difficult. For this reason, the idea to try to obtain this type of estimate is good, but essentially you are lost a lot of information in this estimate. For the reason, Montgomery and Sam tried to say that the power constellation appear in this form. Appear when you when this function st, for example, is bigger many times with this function log t over 2 log t, but now with this new term, right? Log t. This. And essentially, the result says this function is bigger in a special sequence. Is bigger than this function here.
And it's lower to its symmetric.
This is a symmetric. So essentially, you only you have this type of bounds here, but this function is not decreasing, for example, or this is not smaller here. This function has a mysterious spirit here, and this type of result try to say that this function is not simple. This function has a special behavior in this part. And for example, the resonance method of Riemann try to say this. Try to say, okay, you need to put a special polynomial, Dirichlet polynomial here to catch these values here. We cannot say the principal term plus the error, but you can take less values here. And using, for example, this method, you can obtain that how is the behavior of this function in a special sequence here. This is the philosophy that I have about this type of methods. Try to say that we have these bounds, but we need to try to obtain more information, but not in this form, because maybe we lost a lot of information in this type of bounds. Maybe we need to try to obtain lower bound in this form, for example. This is the philosophy that I have. And the idea is to choose a good Dirichlet polynomial. And this is a combinatory argument that appears in the work. Try to use the prime number theorem, trying to use layers primes to try to obtain this type of inequality.
Okay, thank you.
Thank you.
Congratulations.
Thank you, Professor.
So perhaps just to complement the answer, I guess the quest for all of these objects in analysis and number theory is always to find the right order of magnitude of things, right? Main term, and then error term, second main term, and then error terms. Some objects are very wild, and you cannot point what the main term is. For example, these things, and you would settle for upper bounds and lower bounds for the object. So his thesis has two nice components, which he gives upper bounds, but usually these objects are oscillatory. So you cannot talk about like absolute lower bounds because they will cross zero. So that the lower bound would be zero, you know. So we settle then in these cases for saying, okay, the upper bound is here, and we settle for a lower bound on the lim sup. So you see, the lim sup cannot be smaller than this. So this is what called omega results in number theory. So there is a certain sequence of points going to infinity that they will be big values. So this is what roughly this is. So this function is roughly between log t over log t, but the lim sup is bigger than the square root of this value. And then we don't know what actually the truth might be. So this is topics for research.
And one comment that I want to say is that, okay, we cannot write this function like in this form, right? But it's very nice because you can write the mean of this function. You can write this something t log t plus error term. So this is the mystery because you cannot exact information here, but you can information about this. Exactly. For example, the Riemann zeta function has something like this. You have lower bounds, you have omega result for the function here. You cannot find this form for the Riemann zeta function, but you can obtain the information about the integral of the moments of the Riemann zeta function exactly. This plus zero. For this, this is a mystery about this.
Yes. Okay, I now would like to pass the microphone to Professor Gugu for his comments and questions.
Thank you very much. Can you put again this slide on the resonance method? And,
Okay.
okay, no, with the resonance method with this. Yes, this one. So, what is the idea here? You are doing like an average with weights. The idea is that the weights are concentrated in the part where the function is large.
Yes, exactly.
So how? Yes, and how do you choose the? How can you choose these Dirichlet polynomials, which are in some sense more concentrated in the region where the function is much larger than the average? If I understand, the average is of the order of log, no? So it's much smaller than than your omega result. So how do you really find these miraculous Dirichlet polynomials which are just concentrated in these rare regions where the function is very large? So.
Really, for example, in this case of the resonance methods on the Riemann, he showed the philosophy is the following, right? Okay, you need to optimize this part. So, and this part, you need to choose a Dirichlet polynomial. And really, the first idea is you need to choose a function phi, right? You optimize this in this function Dirichlet polynomial and a function phi. This is the first idea. But for example, the Riemann zeta function in this case, using some approximations, you can write the Riemann zeta function like a series. The Riemann zeta like this, something like a special finite series plus error term in the critical line. So essentially, the information about the Riemann zeta function lie in this series here. And here part, the Dirichlet polynomial, okay, you write the Dirichlet polynomial in this form. It's something like this. Let me write in this form. Something like this. Okay, and you do the calculus with this. So essentially, you do this part. For example, this part appears here. And essentially, this is the series multiplied with the power 2 of the other series. So finally, when you do all the calculus, you need to only minimize certain objects, something like this. With some power here, something like this. In this case, you multiply with the R and something like this, right? Because you take the modulus power 2 here. So essentially, you obtain that this part is something like this. Let me write something like this, plus the error term here. If you do the multiplication of this from this. The function phi that appear here really disappear when you cancel, when you divide with this part. The part was, suppose that I will write something like this, right? This is not exactly the expression because it's more big, but I will write something depends of phi. The other part here, okay, you do the calculation, you have the function RT something like this. So essentially, you do the calculation and I don't remember exactly what happened here. I will write alpha. I don't remember exactly the. It's something like this. I don't remember because there are a lot of calculations here. And the idea is now to optimize this quotient, right? This is a problem. The information about the zeta appear with this part, and the Dirichlet polynomial appear with this part. So essentially, you need to optimize this part. This part cancels for this reason. The result independence of phi in the computations, and you need to optimize this part. So essentially, you need to optimize this part here. And so you, this is a problem of combinatory. You need to optimize this part when you take a special function Rn. And so the Riemann in the paper of resonance method, they solve this problem using real analysis. Some tricks, they used some interesting parts when he solved the, and he optimized this part. And he said the maximum of this part is this plus error term. And the reason where appeared the good election with this R is in the tricks when he used.
And is it possible to use this function to describe or to give non-trivial information on the regions where the values of zeta of 1/2 plus it is large? So say in comparison with the zeros. So they have the zeros, and you have some regions where this is exceptionally large. So that the average is like, yes, the kind of describing or giving quantitative information on these regions where the value of the zeta is large, because these weights are in some sense concentrated in the region where this is
Really,
large.
for example, in the papers on the Rajan again, they showed the measure of these t's when it's large. And he used some methods to prove the measure of this t, that these are big. And the tricks that he uses are similar to the optimization of this part. So yes, you can do the measure of these good t's, right? But it is in the resonance methods on the Rajan. But in this case, in the version of Bondarenko and say, for example, in the paper they say that the trick that they use it here to try to optimize this quotient then allows to obtain the measure of these t's. And now I talk with a professor, and they try to explore more about the measure, in this case for the function Sn.
So I think the first omega results of this type were due to Littlewood, on the error. No, but there are much older results on, not exactly on this, but on the difference between the pi of x and the logarithm integral of x. So that this difference oscillates like x to 1/2 minus little of 1. So in both signs. Is there any relation between the methods of Littlewood and this more modern harmonic analysis method?
Well, really, I don't know if there is a special relation, but one of the principal parts when you construct the Dirichlet polynomial here is to use a special election about the function R. And in this election, you need to choose special prime numbers to obtain the optimization of this. So in this part appear when you use the prime number theorem and try to estimate about the primes. In this part when you optimize. This is the relation that I can tell you.
Okay, just two quick questions on what is the so what is the better unconditional bound on S of t? On the S. Just
let me remember.
just S.
Something like this.
No, but on S, S0. So
ST. Yeah.
ST.
ST is log t, unconditional.
Unconditional. Oh,
Yes. This is
good,
the best
but-
that we have now.
good. But then for the other ones, you have much worse bounds. So like powers of t, no, right?
Yes. For
unconditional.
ST, for S1t, unconditional, right?
Unconditional, yes.
Unconditional, we have log t again.
Good.
Yes.
And for S2, no.
For S and t, yeah, you have this type of information, t n
Yeah.
minus 2, something
I
like t, something like this.
Minus 1 on the log t.
Minus 1, this is part, right?
And
Yes,
minus
yes.
1 over log, okay.
Kind of confusing.
So even the exponent is not no. Okay.
Yes.
Good. In the standing conjecture is that Riemann zeta function has no multiple zeros, really, so that n of t is equal to n star of t, right? Is what is expected to be true, right?
Sorry.
So the people, is there a conjecture? So the natural conjecture is that n star of t is equal to n of t for
Yes,
all t,
it's true.
right? There is no multiple zeros at all, right? Okay. So I'm very much impressed on your thesis. I think you made so you used very deep methods, and I agree with my colleagues that you are right. So you mastered this method, so you have no fear to do very non-trivial calculations, and you improved results in a very classical and very central area of analytic number theory. So the results are really very much impressive. For instance, in this constant, so you improve the constant. So you improve more than what has been improved in the whole past history of this. So the distance between 1.333 and 1.32725 is smaller than the distance of your constant to the previous one. So this is really impressive, because this estimate seems to converge. But you could change the third digit, which is really impressive. So thank you very much. Thank you very much, Manuel, for inviting me.
Okay, now, Mike, I hope you are listening. So let's now move the part for questions and comments from Micah Milinovic, who's joining us from the University of Mississippi.
Can you hear me?
Yes, we can hear you fine.
Let me start with a few comments about what the other questioners asked. The paper of Farmer, Gonick, and Hughes, where they conjecture the maximum of the limb soup, or that paper is actually about the size of the modulus of the zeta function, and the S of t is just a comment. So the whole paper is about the actual Lindelof hypothesis and the size of the modulus.
That's okay.
And I've asked them, and they said they could probably conjecture something about the lim inf, but they never bothered to do it. Okay. Also about the derivatives of the Riemann C function and the proportion of zeros on the critical line. That was Brian Connery's PhD thesis. So in fact, the proportion does go to 100% quite fast, actually. Like already by the fourth derivative, you can show 99% are on the critical line. So, and he can show, I think, the nth derivative is 1 minus 1 over n squared or something. So it goes to 1 very quickly, the proportion. So, yeah, that's a very insightful comment. And I guess if it's Brian's thesis, probably Hugh Montgomery had the idea to do that. One other question about your n-star, or the comment about your n-star t-bounds, the question was whether you could maybe find some magic sequence of functions to show 100% of zeros are simple. So I think the flaw isn't in the approximation theory. I think the flaw is in the number theory. So Montgomery's f function, we know how to evaluate it between -1 and 1. And so if you could increase the support to -2,2, then Andrés and his co-authors could then likewise show a much better bound. And if you could increase the support of the f function to -3,3, then they could show a much stronger bound. But these are questions about exponential sums over primes. So it's not questions about analysis, it's questions about number theory. So the flaw isn't in the analysis, the flaw is in the number theory. That's my personal view anyway. Okay. So I guess another thing that might be worth saying, sorry if I'm not asking a question yet, I'll get there. So the resonance method, for the way that Sound of Origin did it, you don't need that weight function phi. You can do it just integrate from t to 2t. And what he did is he just estimated the numerator and the denominator. And then he optimized that. So essentially with the restriction of take the Dirichlet polynomial as long as possible, such that I can estimate both integrals, his method is optimal. So this is kind of like Montgomery saying, suppose the support is between -1 and 1 in the pair correlation problem. And now Bondarenko and Seep said, but we don't have to estimate the integral. We only need to get a lower bound for the numerator, which is exactly like what Andrés and his co-authors did, saying we don't have to have the support in -1, 1. We only need it to be, right, so positive in -1, 1, and then non-positive outward. So in some sense, your improvement of pair correlation is just like Bondarenko and Seep's improvement of resonance. Where you leave the realm where you can get the asymptotic and you say, I just want an inequality now. Anyway, I had a question, I guess, about your linear programming paper. So Kohn and Elkes actually find the optimal functions in low dimensions, like they do in dimension 1, and do they do it dimension 2? I don't remember.
And the dimension
But-
1 is the sine.
Yes.
It's a
So-
simple function, right?
Dimension 2 is
Is
not
there any
known for
hope
this
to do
peer
that
packing.
for any other measure, or is it only for Lebesgue measure?
Sorry?
So they take a function which is 1 at 0, right? And non-negative everywhere.
Uh-huh.
And they say we want the Fourier transform to be non-positive outside minus 1, 1. And they find the optimal, they show there is an optimal solution. It's not unique, but there's choices that give the right answer.
Yes.
So that's, I guess, with Lebesgue measure, and you want to do that for a different measure in your paper, right?
Uh-huh. Yes.
So is there any hope to prove it in dimension 1 for any measure that's not Lebesgue?
Try to explain more the question to try to understand exactly what is the point. He can hear me?
Yeah.
Please try to explore. Try to talk more about that specific question. I don't understand exactly what is.
So you're essentially trying to do the Kohn-Elkes problem.
Uh-huh.
All you've done is change the measure, though, right? Because it's the same conditions on the function, but now instead of just integrating Fourier transform, right, you have kind of this absolute value of alpha that comes into play, right?
Uh-huh. Yes.
So you can just think of that as being part of the measure. And you're getting sort of nice bounds with your Gaussian times a degree 82 polynomial. But can you take anything simpler than that and actually find the optimal solution? Or can you only do it when the measure is Lebesgue?
No, I don't know.
Okay.
No, I don't have an answer for this.
Okay. I mean, I think it's probably a very hard problem. I just didn't know if you had thought about it. I do have a question, I guess, about your omega theorem result.
Okay.
So I think for S of t, you need to use RH, but there are omega theorems for S1 and S2 that are unconditional, that are almost as strong or maybe as strong as the RH bounds.
Yes.
So have you looked about, so I think in fact Sang has an omega result for S1 unconditionally that's as good as RH in a later paper. So have you looked into removing RH from your bounds for, say, S1 and S2 and higher?
Remove RH for S1, right? Or for all
Yeah.
Sn. Well, S1, specific S1.
Or maybe for Sn for n large enough or something like that.
I think that the problem with Sn is this part, unconditional is this part of the polynomial with the zeros outline of the critical line, right? This is
So
the,
S1 would be the only thing to do it for.
Yes.
Okay.
So in the case of S1,
Sang did the Montgomery style omega theorem.
Yes.
But what about the improved size using Bondarenko-Seep?
Yes. One of the Let me think about this. For example, the convolution formula that we have, we don't
Right,
need
you would have to use zero density estimates or something, right?
Yes, you need to use something of this. Yes, I can use this. This is in the convolution formula.
But I mean, conceivably, that's exactly what Sang did. He used a convolution formula and he used zero density to estimate the zeros off the line.
Yes, but
Might be worth thinking about because, of course, removing RH makes the theorem actually a theorem.
yes, 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 yes. I will think about this. This is a good new project. Oh, yes.
That was the right answer, right? That's a good new project.
Well, when you solve it, acknowledge me.
Or better, invite you to be a co-author.
Okay.
Anyway, I think your thesis was beautiful, and
Oh.
thank you for asking me to be on the committee.
Thank you so much, Professor Micah.
Thank you, Micah. Okay, so can we put perhaps
I will.
back in your PDF? Well, I wanted to first thank you all for agreeing to be part of Andrés' thesis committee. It's always a pleasure to have you here. Before I open up to questions from the audience, I just wanted to say a few words about Andrés' work. I don't have actually any particular question. I have seen the work over the last 4 years, so I am pretty much I learned what I had to learn, and I asked what I wanted to ask, and he answered what he could answer me, and I'm pretty much happy with the outcome. Well, you know, for all the students that are present here, and for Andrés, and for all the students that are watching us on YouTube, I just want to take this moment to talk a little bit about the trajectory here of Andrés at IMPA. I guess he arrived here 4 years ago, coming from the master's in Lima. And it was very, particularly apparent to me from the very beginning that he came here to IMPA. For those of you who watched the movie of Rocky, he came here with the eye of the tiger, he wanted really to do his best. I mean, not in a competitive way, like being better than others, but in an absolute terms. He wanted to come here and do the best work that he could do. So it was a pleasure to me to oversee his work, to work with him over these past 4 years. I mean, to see how devoted, how hardworking he is, how intelligent he is, how such a good listener, brings good ideas, great ideas to the table. You have seen from his presentation that he has absolutely no fear at all of big computations and technical insights. And this is really part of a mathematician's life, whether you like it or not. Some people like it better than others. But there were moments in our joint ventures where we would discuss a certain particular object. And I would just look at this and, hey, man, to me this is not tractable. And he would say, well, just give me some time. And then he would come back like 2 weeks later with computations. And we're right, we had to do some cleaning up, but it worked, So in his second paper where he extended, the results that he presented here for the critical line are, of course, the most classical, and it makes more sense to present them first. But when we had to move to the critical strips, all of these special functions that come into play, this optimal band limited majorants and minorants, you have to actually open them up and work with the explicit Fourier transform of these functions, which are very hard and complicated, very hard. And we managed to write an 80-page paper with Micah, me, Andrés, and Mike, and then we could shorten it up. But at the latest version, it was like a 42-page paper. But still, a lot of Andrés' hard work went into those papers. I am very grateful that I came to work as his collaborator and as his advisor. I think his case here is a model, is really an example of a great PhD from beginning to end, of a person who came here highly motivated, highly intelligent, did all the courses, gave his best in all the courses, passed the qualifying exams, quickly moved to the thesis stage, started looking around and having always a critical eye on things, talking to his advisor. And not only that, but his strength also always comes, and this is something I would like to encourage in all of you, and talking to people. Mathematics is talking to people, talking to your professors, talking to your friends. I mean, there's always someone out there that has some sort of knowledge that you need, that you might want. So you see Andrés has collaborated with a certain number of people, and people have taught him things. He have taught other people things. He has been through a lot of experience, and I think this sort of experience has made him a better mathematician and a great researcher. He has had chances to travel a bit and do an exchange program with supervised by Mike at the University of Mississippi. He spent 3-4 months last year in the United States, where he had chances to deliver lectures, seminar lectures at very nice universities like the University of Mississippi, like Stanford, Caltech, UCLA. So he visited these places. He talked to Soundararajam himself about these methods and presented his work. And so, I mean, this is what everybody should be aiming to do. I mean, there's a stage where you do your qualifying, you study, do the preliminary courses, do your qualifying exam, but then at your thesis stage, move around, talk to people, think about things. Anyway, in conclusion, I have absolutely only fantastic words to say about Andrés. It was really a pleasure to me to be his advisor. You know that recently, I mean, as a statement of his success, I think his thesis was outstanding. As you may see, very little influenced by me. I mean, it's essentially 100% his own work, his own ideas. Over the last few months, as I was saying, as a statement of his success, he received a very nice offer, a very nice postdoc offer to go on with his studies in the next step. So I'm glad to announce to you, if you don't know yet, that Andrés, pending the approval of this committee in a few minutes, is going to a postdoc in Norway, the Norwegian University of Science and Technology, for 2 or 3 years, starting this September. As a matter of fact, sponsored by Christian Zijp, which he mentioned here in this talk. So Christian Zijp is one of the absolutely top analysts for our time. And he runs the analysis group there, which is one of the top analysis groups in Europe, with other 3, Bondarenko, Malinikova, some very top mathematicians. And it's going to be an amazing experience for Andrés to have the chance to interact and learn more with these colleagues. So it's really, it was really an excellent experience for him. I hope you had a good experience at IMPA. I hope from this moment on, IMPA will become your alma mater. So I hope you'll look back to this place and always remember of the friends that you made here. Always keep your good memories. And, well, this is, as you know, from now on, your second home. You're welcome here and anytime that you want. And I'm sure my colleagues from the committee will join me in saying that we expect great things of you. We expect you to develop a nice role in the mathematics wherever you choose to be later, either in Europe or back in Brazil or back in Peru. But we'll always be at your side to help you and be together in this journey, man. Okay, so these are my considerations. I would like now to open up the space to questions from the audience or comments, if anyone wants to speak a little bit about your friend Andrés. As I said before, we will open up. I won't open up this time from questions from YouTube, maybe in some future opportunities, but since this is a pilot project, and we kindly volunteered Andrés' thesis to be this pilot thesis on this live broadcasting project. So now let me momentarily close our session. Okay, so we're going to stop the movie, the filming now. We're going to come back in 5 or 10 minutes, and I'm going to invite you all from the audience to leave the room momentarily and leave just the committee here to deliberate, and we'll be back in 5 minutes, okay? Very well. We are back here with the defense of Andrés. I am very happy to give the good news and say that our committee deliberated and, of course, unanimously approved Andrés' thesis. So join me in congratulating our new PhD from IMPA. Congratulations for the excellent work. This is the papers, official paper signed by all the committee members. You will turn in this into our graduate school, and this will become your PhD diploma. So, again, I guess this closes our session for today. Thank you all for being part of Andrés' PhD defense. We are going to have a small celebration tonight, I guess. Maybe I'll let Andrés invite you. If you want to say a few words for your committee or invite people and say...
Okay. Let's go. Let's go to... What's the name of the place? I don't remember.
Cobal at 8 o'clock, no?
Cobal, ne? Cobal or... East. Okay, let's go to Cobal, 8 p.m. Let's go.
Certo, né? Ok, we're done. Ok, vamos lá. Você tem que assinar aqui.